Hello, this is Ben. Here we are going to talk about street racing tech, I guess. A lot of people kind of neglect their oil pump. The modification they do is pretty much high volume and put it on. And sometimes they put on an oil pan. So it's very, very simple. And somehow, sometimes that can bite us the hard way. And I'll show you guys why. And how serious this could be, and we can't really take it for granted by all means. Now, what we're looking at here is a big block Chevrolet. Typical small and big block, excellent oiling systems. The factory and the aftermarket, pretty much the same layout, because why mess with a good thing? Okay, so short of bushing the lifter boards and all that, everything's basically the way it is. It's a very, very sound design straight from the factory. Now, what we're looking at here is a 672 cubic inch big block Chevy aluminum block. Same thing here. The oil pump is on the back. It's a short distance from the oil pump to the oil galleys, you know, straight to the crank rods, lifters, camshaft oil. Very, very effective. Not only that, it sits on the back, so when you guys take off forward, all the oil goes to the back. It is sitting right there where it should be. The Ford's sitting up front, and then when you take off going that way, all the oil goes to the back, and the doggone pickup is on the front. Kind of like, well, what are we guys thinking about? Anyway, now this is very basic. The oil pump pickup is always submerged on the oil, as it should be. And unlike the Chrysler, where the external pump is over here on the driver's side, and I think the Buicks, and of course the Ford is on the front, but submerged. And the LS engines, since they inherited the Ford 10-bolt cylinder head pattern, 10 bolt holes. Wow. Okay, and you also put the pump towards the front, driven by the crank. I wish they would have put it back there, as they traditionally do, but they went to the front, and now you have a long pickup to the back. That's why maybe they eventually switched to dry sump on some of these Corvettes, because when you got lots of horsepower, you start having issues with windage and everything else. And I'll show you how some of these oil pans I have 1, 2, 3, 4, 5 oil pans, and 4 of them are defective, and I'll show you why in a little bit. Now, going back to this, windage losses is quite significant, and that will tell you later on if you're going to have to go to a dry sump, especially when you're bringing the engine 7,500, 8,000, 8,500. It's kind of hard to retain that wet sump, and I'll show you what happens with them. Now, on the windage, I prefer having a kick out, all right, with one of these. A crank scraper that's bolted on the side of the block. And then you bring this throws, this little strippers here. They say about 40 thousandths. I bring it closer, more like 25. All right, because the rod and crank's not going to move 25,000. The closer you can get it, the better you can strip the oil out of the whole rotating assembly here. And once it keeps turning and turning and turning, and there's a cloud, your windage loss is going to be worse. And not only that, the oil gets beat up like it's been placed on a blender. Okay, and let me show you something here real quick. I shook this one earlier, testing this camera, but you can see it's somewhat dark here on the bottom. But if you look closely, there are no air bubbles, even on the top part. Okay, so this is an oil in its dormant state. Now, when that doggone thing is turning, that becomes like a real big blender. And I'll show you later on. Again, there are some design elements here that I don't quite like, but here you go. So when you take the oil as a sump and you do this, that's exactly what happens. All right, you can go this way. That's like the crank throws and rod hitting the mist of oil, or the oil drops are getting smashed, and look what happens. Highly aerated. Okay, you can see little tiny bubbles. I don't know if you can see that on, but there are tiny bubbles all over the place. Okay, now, if oil stayed dormant on the sump, sitting there ready just to be drawn in by the pump, then we have hardly any issue. But since it's been stripped and shook and aerated like a blender, what happens is the Superior with the Chevy oil pump location, unlike the LS, the pickup is short. That is very important. The Chevy, traditional Chevy, the pickup is like a little tube here, and you weld the pickup to the cover plate, and it's that short, perhaps 2 inches. The Ford sitting on front, and then when the car takes off, all the oil goes to the back, sucking in air, aerated oil. Now, what happens when the oil is aerated? Here's the scenario that's even worse. This is off a Ford rear sump layout 351, 302. See this long tube here? What happens is that if you could put a clear pipe in there and watch it on the dyno, you're going to see the oil in its aerated form pulling, shearing the oil column. And guess what comes along first? The air molecules, because it's lighter. In fact, when I shook that, you see the air bubbles go up real quick, real fast. It's okay if they go up, so that the pickup is sucking in solid 100% oil without much aeration. But the truth of the matter is, this is continually blending the oil like a blender, and it's trying to pick up here. So what you're going to have is a column of air, oil, air, oil, air, oil. So the pump is going like this. Okay? When it sees some air, it speeds up a little bit, and sees a column of oil, it slows down. Just like when you try to prime the pump, you know, with your air drill or electric drill, going, as soon as the oil pump catches, slows down. Same thing here. Okay? So while it's going air, oil, air, oil, air, 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 oil, oil, this is shaking, and boom, the shaft breaks. Then it's over. But what can we do to prevent that issue? It's got a lot to do with this. Good performing oil pump pickups doesn't have this very fine screen. The very fine screen allows the air bubbles to go in faster than the oil. Okay? When you have a fine screen, when you buy this new trick part of the week, and the pickup is fine screen, beware. The fine air bubbles will go in, and then the oil will get stuck in there and have a hard time going in. Now, here you go. Here's an aftermarket. Pretty darn good design. Okay? Of course, when you look at that, you go, oh, that's not doing anything. I see a lot of guys complain about, that's not really doing anything. It's a horrible design. Well, it's not. It's there to stop some debris from jamming out the oil pump, but the main purpose is to let in oil go in between the pump running it, pulling it from the sump. Okay, so if it's too restrictive, the holes are too small, the air molecules that go in, the oil gets lagged behind, and that's when you have trouble. Then you're gonna have starvation. Happens a lot at high RPM. Okay, that is clear. Now, I'll come back to this. I'll pull this over here right now, and we'll talk about the crank. What happens when we need to switch over to a dry sump. Okay, let me push this away quite a bit first out of the screen, and I will pull up our stand and show you the oil pump. Now, we have issues with this oil pan that I've seen. Let me look at my time. Okay, here's the deal. I covered the name of the pump, it's the oil pan manufacturer. Okay, and let me bring this closer so you guys can see the issue at hand. Here we have a pretty good oil pan with all the baffles and all the fancy trap doors and stuff to keep the oil pump pickup fed with oil. That's excellent. No, nothing wrong with that. But here's the main problem that we have. All these oil pans. See this one here? The scraper. It's supposed to stop the oil from coming up and going around again, because it's turning this way, going around again and catching the crank. This is supposed to stop some of the oil from climbing up the side of the block and getting caught up with the crank and creating windage losses. Let me show you what happens. There's like a column of oil here, huh? Look what happens. Where's there? Okay. What happened there? What happened there? And that's a good company oil pan. The stitching on the weld is not quite out there. So really it's still going to go in there and go up and get reintroduced to the crank and create windage losses. Here's another quality oil pan. Very fancy. We have this situation at hand as well. Okay? Same thing. And let me bring another one. There's a front sump forward. Okay? You guys say it's not too bad here. Not too bad, but here. So you also have that issue. Now, what do we need? This is what we need. Right here. No windage tray, but it's got the kick out right here. Kick out on the passenger side. Very important. Okay? When you have that design, all the oil gets thrown in the side in this little pocket and it's collected. There are no fancy things there that it's not welded completely. This catches the oil. There's really nothing going on here. The oil gets thrown in and caught up right here. You have to have a kick out, okay, for a wet sump. And the ultimate one is when you have an oil pump pickup. I mean, you have there's a small block Ford, that one there is a Chevy. It's got a kick out right here on the side, catches all the oil, and it's got a custom built pickup there. Okay? And I can't take it off, it's welded, but if you look at that screen, it's very coarse. It looks like chicken wire. Real coarse chicken wire in there. Okay, and it goes down here to the external oil pump. Now, that is the best possible scenario short of a dry sump. So, there you are, guys. You've seen what is going on. I'm not too happy with the oil pan manufacturers as it sits. A lot of them have a defect. It's even worse when you don't have a kick out and the scraper's there for decoration. Okay, now we bring back Mr. Big Block Chevy here. Now, remember what I said This doggone thing is the cranks are designed quite ineffectively, or should I say, just flat out wrong. There are companies out there, just like cylinder heads, when they advertise their flow rates, the more expensive one tends to really show what they're doing. Okay, that when they claim theirs flow 400, it will flow 400. Some of the budget mass production head that claim 340, 350, quite short. Sometimes they're in the 310, 320 range. So not quite as they claim to be. Same thing with the oil pans. Okay, good quality pans, sure, you got no doubt it's gonna work good. Now we're gonna talk about this block. Okay, the crank, like I was saying. Let me move this camera, guys, and I will bring you close to this thing. Now, just bear with me as I show you what's going on. Now, I think it's turning this way, okay? Looking up the front of the engine is going clockwise. You notice that the crank has got a little arrow tip here, okay, and blunt on the trailing edge. So it's turning that way. It's blunt right here, and the front is so-called aerodynamic. And this is backwards, okay? A lot of you don't understand. This is backwards. Okay, blunt on the end part, turning that way. Now, let me reinstall this camera on the stand and let me go to my screen to explain why it's backwards. And it's quite obvious. Now, why is it backwards? Basic. Oh, well, okay. Let me make something clear. A lot of guys out there racing in NASCAR, F1, Indy cars have aerospace background. And I've always suggested to people asking me, what did you take? What did you do to get to where you're at? Well, you just can't be a basic automotive guy. You have to have some kind of aerospace background. That's very important because the understanding is a little bit different. Now, speed entails aerodynamics, okay? And how the air functions around is very important, how this is happening. Now, what you're looking at is an how should I say? Nature dictates how a form should be shaped when it's cutting through the wind. There's no better example than a raindrop. If I would have had this thing this way, okay? Coming down from the sky, a raindrop starts around here on the leading edge and tapers off, okay, to a fine tail. That is what nature wants that object to be in order to be aerodynamic or to cut through the air effectively. This is the other way. This is like the edge of the crank, the leading edge. Sharp, and then goes through round on the back. That round back is called the cam tail. The cam tail creates a turbulent wake right like it is here, and it's a low pressure region and has a pressure drag, meaning the pressure drag is when it's pulling away. This low pressure behind it's trying to snap it back on, okay? It's not a hydrodynamic drag, but more like an aero drag, like when you go through the air with your car and it's got a big back end there, you see a lot of wake, turbulence. That's what you call a cam tail. Now this crank, what you're looking at, it's got a sharp leading edge, like I showed you earlier when I brought it up, and a blunt as exemplified by this drawing here. The oil mister here, it goes in, and suddenly this abrupt end like it is there. This cut creates a camtail scenario. A pressure drag, turbulence is the byproduct of this design. Just imagine, okay? At high RPM, this thing is turning around so fast. It becomes a fan in itself, like a vacuum pump. Those drastic camtails on the crank throws create so much low pressure area that when this is right side up, right, you have the pump. Just think about if you have bad windage, bad baffling in your pan, everything is crazy here. It's what a zoo. It's spinning and everything is getting thrown off. Well, one thing is consistent. You can start to create high pressure here from blow by, you know, all that stuff. If you don't have proper venting, or even if you do, there's always some kind of positive pressure inside the crankcase. Okay, from the rings and all that coming through. That positive pressure is in the mist inside that oil pan. Now, we know that high pressure goes from high to low pressure. It sees high pressure, it goes to low pressure. Guess what happens when you're spinning? This crank, this counterweight, a lot of, what do you call that? Low pressure weight right here. The pressure drag, trying to keep it from rotating easier. But the turbulent weight creates a low pressure area. Right there, right there. And the high pressure area is here within the crankcase. Guess where they go? Right behind that crank. I remember one time I saw a video, I gotta look for that, of a NASCAR FE engine with a see-through oil pan. At 7,500 RPM or so, it shows the oil pump pickups there, some kind of aerated oil. And eventually at high RPM, and they said now it needs a dry sump. High pressure from the crankcase migrated to the low pressure. Remember that high pressure crankcase has got a lot of oil mist suspended within its vicinity. They all go to the back end of the crank throw, right here. All that mist starts to form. Right behind this crank throw, that crank counterweight, this crank, that, and it goes through behind. And guess what happens to the crankshaft? At high RPM, the pickup starts to get drier, it starts to get lower and lower, everything's suspended, and the crank disappears in a cloud of oil. The reason there's a cloud of oil there is this scenario. The camtail is so vast at 7,500 plus 8,000. It's spinning so fast, it's creating this vacuum situation. You got a high pressure crankcase, low pressure camtail. The oil doesn't drop straight to the pickup to get collected again. It stays on the crank and the crank disappears in this cloud of oil. Bad scenario. It happens with a small block, happens with a big block. Perhaps worse on a small block with a stroker crank, because your crankcase volume is a lot less. Not like if you had a big block, you got a big crankcase, you got a little bit more working room there, okay, for the pressure to go someplace or to drop off to the sump. But on a tight crankcase scenario with a big 250 crank or 4170, even a 4-inch, you don't have much room there, man. You got a big counterweight with a camtail there, drawing all that oil. It becomes a scenario, and that's when you start burning your bearings. And then you go, oh, it's the oil pump's fault. Well, yes, it is. It's probably not as efficient. Not only are you trying to draw in or suck, I hate to say that word, it doesn't happen in engineering, trying to suck all that oil from the sump, but it's an aerated form because of the long tube, not like a Chevy with a short one. It's not quite as susceptible to that situation, but the long tube, you have this air oil, and mostly, especially when you got this doggone very, very fine mesh that everybody wants because it traps good stuff. Yeah, even oil. Now, Eventually, you're going to say, I'm having bearing issues. Sure, your counterweight created some of that besides the oil pump being inefficient at high RPM. This got a lot to do with it. All right? So if this is if I would do something, I would have had this thing rounded off. Okay? And then perhaps on the trailing edge, a little bit round off too. Because you know what? You can't really taper to like a trailing edge here. The reason you can't put a trailing edge here, then the counterweight has to be extended. Okay? Because once you cut weight off here to give it a taper, so it ends up looking like this, your crank will look like this. It's going to be hard to balance the whole doggone crankshaft because you don't have too much mass here to probably weigh the, it probably could be done. But then again, there's also a scenario here where the air comes in, and if it's too steep of a, just like if you put this in here, if you reverse this situation, you put a pointed tip there and a pointed tip here. When you have that situation, when the air goes through, I think it's anything more than 15 degrees, 12, 15. It's been a while to have my notes in aerospace. You have separation. When you have separation, then you also create a wake because the pulling is too harsh, too quickly. And it's like a 15-degree taper. It's not too bad. The air will come in, hit it, and slowly it'll adhere to it. But once it's a drastic pull down, it goes like this and starts creating that turbulent wake, which eventually ends up similar to that, though not quite as bad as this form. So I think this is pretty much a clear description of what's going on between our things, you know, what's at stake here. So when you look at, I don't name names, there's a couple of companies out there with the correct counterweight as per aerospace understanding, like what I'm studying in school for. They have the crank counterweights in the proper shape. Almost everybody got it in reverse. Okay, you heard that. Almost everybody got it this way. I bet you guys have it today. When you look at your crankshaft pictures, you got the blunt end on the trailing edge, and you have the sharp one on the front. Just like we engineers. When we look at a race car, everybody looks at the front end of the Ferrari, they go, oh, or the Corvette, they go, oh, that's a fast looking front. That looks like it's a fast design, less drag. I don't care about the front. I look at the back of the car. What is the actual, if the back is tapered real nice, then I'll look at that. That's my concern. I look at the back of the car, and most engineers do look at the back of the car, not the front. The front's just like a pretty picture. It doesn't give you the whole story or the picture of what's really going on. Anyway, I hope this is clear, guys. And please subscribe and like my videos, and I'll try to give more information out there. Okay, I do a little bit of dyno. I do more track racing and everything than flow bench testing after I've taken that test. I run the car, see what it does on the track, and then I'll go to the dyno. Okay, and look what I have. Anyway, if given a chance. All right, thanks a lot, guys. We'll see you again. Thank you.